Section: Introduction. In this section, we describe the training process of modern large language models, LLMs, which typically occurs in two stages. First, we train a tokenizer that converts frequently occurring character sequences in the training data into tokens. Then, we tokenize all training text, transforming it into this token vocabulary, and train a model to predict the next token based on the preceding ones. The tokenizer acts as an initial compressor, reducing the length of the text and potentially enhancing the training process. However, this two-stage method has a significant drawback. When we encounter text from a new target domain, the quality of compression decreases, the context length and inference costs rise, and the semantic alignment weakens. This issue is particularly noticeable when we apply LLMs, which are mainly trained on English and code, to molecular sequences like proteins. Although these sequences use the Latin alphabet, their substrings have different meanings and frequencies compared to natural language, leading to semantic misalignment. To address a similar alignment challenge for low-resource languages, researchers have suggested using an algorithm called fast_align, which relies on parallel data from both the training and target domains. While this method shows promise, obtaining parallel training data is often difficult or impossible, as seen with protein sequences and natural language, where no standard parallel translation exists. In our work, we introduce the Sparse Sinkhorn Token Translation (S2T2) algorithm, which does not require parallel data. Instead, S2T2 learns to translate tokens from the training domain to those in the new target domain using only sample data from the target domain and the pre-trained LLM weights. After training a tokenizer on the target domain, S2T2 translates each target domain token into a sparse distribution over training domain tokens, predicts the next training domain token using the pre-trained LLM, and then translates that token back into a sparse distribution over target domain tokens. Our experiments with English LLMs show that S2T2 effectively initializes continual fine-tuning on protein sequences, resulting in better compression and perplexity compared to directly fine-tuning the pre-trained model. Additionally, S2T2 allows for weak to strong model transferability, meaning that translations learned for smaller, less expensive models can be applied to larger, more powerful models, providing benefits at a lower cost. We also outline the mechanics of translating tokens with S2T2, considering a pre-trained LLM with a specific vocabulary size and embedding matrix. For a given input sequence, we represent it as a matrix where each row corresponds to a training domain token. We define a joint probability matrix that helps create a new target domain LLM with adjusted embedding and language model heads. This adjustment ensures that the new and old token embeddings are on the same scale, simplifying the translation process. An overview of S2T2 is provided in the accompanying figure. Section Summary. In this section, we introduce the Sparse Sinkhorn Token Translation (S2T2) algorithm, which addresses the limitations of traditional tokenization methods by enabling translation between training domain tokens and new target domain tokens without requiring parallel data. Our experiments demonstrate that S2T2 enhances model performance on protein sequences, improving both compression and perplexity, while also allowing for effective transferability of learned translations across different model sizes. Section. Since it is difficult to directly parameterize a joint probability matrix $P in C, mu, nu, $, we instead maintain a dense weight matrix $C in R, V times U, $, and recover $P, as the solution to the following two equivalent optimization problems. Notice that EQ, opt2 is the $L_2 constrained optimal transport problem, which is known to generate sparse solutions. Moreover, since $C equals C_1 cap C_2 for the convex sets $C_1 equals P in R underscore plus caret B times U, P 1 equals mu $, and $C_2 equals P in R underscore plus caret V times U, P caret top 1 equals nu $. These problems can be solved using iterative Dijkstra's projections, a Sinkhorn-like algorithm via with guaranteed convergence. See alg. Sparse_Sinkhorn. In every Sinkhorn iteration, we solve a set of $L_2 projections onto a probability simplex. This optimization problem enjoys an efficient backpropagation computation. A small caveat is that we are not always projecting onto the unit simplex but rather onto a scaled simplex, so the optimization is modified accordingly in alg. Sparse_Max. Begin, algorithm. %latex2 HTML id marker 687 caption, Sparse Sinkhorn I. Point 1. $end for state return $x $n+1. $end, algorithmic. End, algorithm. Begin, algorithm. %latex2 HTML id marker 710 caption, Sparse_Max, Beggy. P_I equals max, z. _I tau, z, 0. $end, algorithmic. End, algorithm. To learn our token translation, we initialize the weight matrix $C by setting each entry to be $1 per V. Obtain the joint probability matrix $P by applying alg. Sparse_Sinkhorn to $C and therefore nor forward values in $P. During the backward pass, we differentiate through the Sinkhorn iteration and update $C directly. In practice, we find that iterating $3 times is enough to generate an effective sparse $P. In this section, we explore how to find a joint probability matrix using a method called Sparse Sinkhorn. Since directly working with this matrix can be challenging, we maintain a dense weight matrix and derive the joint probability matrix as a solution to two equivalent optimization problems. One of these problems is known to produce sparse solutions. We note that our weight matrix is defined by two convex sets, which allows us to solve these problems using an iterative method similar to Dijkstra's projections, ensuring convergence. During each iteration of the Sinkhorn algorithm, we perform a series of projections onto a probability simplex. This optimization is efficient for backpropagation. However, we must remember that we are projecting onto a scaled simplex rather than a unit simplex, which requires some adjustments in our algorithm. To learn our token translation, we start by initializing the weight matrix with equal values. We then apply the Sparse Sinkhorn algorithm to obtain the joint probability matrix and proceed with a normal forward pass. In the backward pass, we differentiate through the Sinkhorn iterations and update the weight matrix directly. We find that 3 iterations are typically sufficient to create an effective sparse joint probability matrix. For our experiments, we use the UniRef50 protein sequence dataset with the OLMO-1B English language model, processing batches of size 16 and a context length of 512. Our training tokens are single characters, while the target domain uses a new byte pair encoding tokenizer trained on UniRef50, which reduces the length of protein sequences significantly. This reduction impacts the model's compression efficiency, measured in bits per byte. To manage the sparsity of the joint probability matrix, we introduce an entropy regularizer to our loss function, where a larger regularization parameter encourages sparser solutions. We compare our approach against 4 baseline methods, ensuring we maintain consistent training practices using the AtomW optimizer. We set specific learning rates and weight decay values for different training phases, and we utilize a cosine annealing scheduler for learning rate adjustments. Our results indicate that initializing with our method yields better language model quality and compression compared to traditional fine-tuning methods. Notably, our approach outperforms both dense Sinkhorn and unconstrained token translation. After fine-tuning, we also see improvements in performance metrics compared to direct fine-tuning with a new tokenizer. Additionally, we demonstrate that the translator we learned can be effectively transferred to a larger model, achieving significantly better results than random guessing or using the original tokenizer.